your second lesson for the day, so this is day 1 in the course, and your second lesson of the day is on relative motion. Now, I want to go back to yesterday, or to the first lesson of the day, because there's something I could have been a little clearer on. I said that you had 2 ways you can do vectors. You can sit there and draw the vectors, and then all you have to do is measure the tail of the first line that you drew to the tip of the very last line that you drew, and that would be your displacement if you measured the distance between those 2 positions. And then you could just measure the angle. So the only problem with measurement is it's not as precise, and I don't care if you want to use that technique, that's fine for this course. The other method I showed you is components, where you take all of your different vectors that you did, you add up all the x's, all the y's, and you draw a triangle at the end. Okay? Then what you use is Pythagorean theorem to find c. C would be equal to the square root of 26.9 squared plus 33.2 squared. I'm not sure if those were the right numbers or not, but I'm going to throw them in there. And if you calculate C, that will tell you the displacement that the person had during their trip. Now, I also said that this is a vector, so we need to have a direction. So we need to find this angle right here. And the way that you do that, excuse me for a second, here we go. Getting lots of emails right now. The way that you do that is you set up the formula theta equals tan to the negative 1 opposite over adjacent. So the opposite to the angle would be 26.9, the adjacent would be 33.2. So what you do in your calculator is you hit second function tan, and you'd have calculated 26.9 divided by 33.2. And if you do this, I believe you get 39 degrees. So your angle would be 39 degrees north of east in this case. So east would be in this direction, north would be in this direction. So we have 33 or 39 north of east. I hope that made sense. If you have trouble with the problems, ask me and I can do a full problem for you. Okay. What we're getting into now is relative motion. This is a small section of the course, but it's very important in physics. So if we start from the point of view that you are sitting in a chair in your house right now and you think you're sitting still, well, you're not. Because it depends where you're watching you from, whether you're moving or not moving. Because if you were on the moon and you were watching you on Earth, the Earth is moving. Okay, so the Earth is moving, our solar system is moving throughout our galaxy is moving throughout the universe, so in a sense, you are in motion. So the whole point here is in physics, is you have to know what your point of view is, or where you're looking from. I'm going to set up a scenario that I hope sort of summarizes everything from the second lesson of the day. So, a person is standing on the shore. The water moves, so the water could be a river. The water moves past the person at 10 meters a second east. So this is a good example of where direction is important. A boat on the water moves at 20 meters per second east. A person on the boat moves at 15 meters per second west. So the question is, how fast is the person on the boat moving? Well, it depends where you're standing. If you're sitting in a chair on the boat, you think the person is moving 15 meters a second west. But what does the person on the shore think? Well, what we can do is we can add up all of these vectors. So we can take the velocity of the water plus the velocity of the boat plus the velocity of the person. I don't do it the same way that they do it in the lesson. I use a more simplified version. You can use whatever works for you. So if we call east positive and west negative, we can solve this problem. Now in physics, you can set the parameters of positive and negatives when we use them, but usually east is positive and west is negative. North would also be positive and south would be negative. But you can set it up any way you want. So we say the water is moving 10 meters a second to the east. So that's plus 10. Then we have plus 20 meters a second because the boat is moving 20 meters a second. So it's additive. The water and the boat together make the boat seem like it's going 30 meters a second. Now the person is moving west, so that's negative. So from the viewer who's sitting on the shore, it would look like the person on the boat is moving 15 meters a second to the east. Okay, so all you have to do is add up all of your velocities and it will tell you relative to the person on the shore, the person on the boat looks like they're moving 15 meters a second east. Relative to a person on the boat, the person moving on the boat looks like they're moving 15 meters a second to the west. So the whole point here is it all depends where you're sitting in physics to get your frame of reference.